So LeChatelier's principle is heavily used in chemistry, and it all comes down to this idea that when you have a system at equilibrium where the forward and the reverse reactions are occurring at exactly the same rate, if you subject that system to a change, some external perturbation, LeChatelier's principle states that the system is going to shift in response to that perturbation in order to re-establish equilibrium. And so we're going to talk about a variety of possible perturbations, but we're going to start with concentration. So what happens when you add more of a reagent or more of a product, or you remove one or the other? How will the system shift to re-establish that equilibrium position? So let's start with this example. This reaction is probably the most important chemical reaction in the world. It's known as the Haber-Bosch process, which I may talk about in class. This is a really powerful reaction because it was the first to produce ammonia, and ammonia is then used to grow food. And so a huge percentage of the nitrogen in your body comes from plants that took the nitrogen from the Haber-Bosch process. And so this is really a reason why so many of us are alive. Problem is, this reaction is not very easy to have happen, and you can look at the K here, which even at 700 K at really elevated temperatures, it's only 0.291, which means that it doesn't even favor the product. So let's start with the condition where the system's at equilibrium. So just taking these numbers, you could punch these numbers into the expression for K, and they would add up to 0.291. So this is a situation where Q, the reaction quotient for the system, if we were to punch those numbers in, is equal to Kc. So the system's at equilibrium. But let's see what happens then when we change any one of these particular concentrations, what the resulting effect in the reaction is as it searches to reestablish equilibrium. So let's start by just kind of thinking about if this is our situation where we are at equilibrium, everything's nice and happy, forward and reverse are dynamically in equilibrium with each other, but then let's say that we want to add more nitrogen to the system, which means that in this Q expression, that nitrogen value is going to increase. That means we're going to increase from 0.5. How can we think about what's going to happen to this? Well, this will no longer be true. Our Q will not be equal to 0.291 or K. It's now going to be shifted away from equilibrium. And the direction is that we are going to push this equilibrium this direction because we're adding more of this nitrogen gas. And if we're increasing the value of 0.5, what is that actually doing? Well, it's going to decrease. If we're increasing the value of the denominator, it's going to decrease the value of Q. So now Q is going to be less than K. If Q is less than K, how is the system going to have to respond? Well, if Q is less than K, that means that the system is going to have to make more of the ammonia here in order to rebalance that value so the system becomes equal to 0.291. That means that this value's got to increase, that value's got to increase. That means the reaction gets pushed further to the right than it was before. But what that does is now Q starts to reapproach K until Q is equal to K. And so that's how the system would respond to a change in concentration of N2. And that response is what LeChatelier was first trying to characterize. So then generally speaking, if we add more nitrogen or we add a reactant, the equilibrium system is going to shift to the right. What that does in principle is it will eat up or decrease the concentration of that N2 we just added, and it will increase the concentration of the products, thereby rebalancing that expression and setting it back equal to K. Well, what about the addition of more hydrogen gas? Well, the same logic applies here. If we pump in more hydrogen gas, that means this value here starts to increase again, our hydrogen, this value increases, which means that the whole system, Q, starts to become less than K, and it starts to shift to the right in order to produce more of this, make this value larger, and rebalance it such that the system remains at 0.291. So generally speaking then, we can conclude that if we add more reactant, then we are shifting the system towards the products from left to right. What if we add more ammonia? So now, what if we have a reaction vessel and we start to ramp up the concentration of ammonia? So we start doing that. Now this value starts to increase in the numerator. If that increases and the others stay the same, then K gets bigger, which means that the whole system needs to shift back to the left in order to rebalance and reestablish that ratio of 0.291. And so sort of by deduction, we can say, well, if we add more products to the system, then the whole equilibrium is going to shift to destroy some of that excess, create more of those reactants to reestablish that equilibrium ratio that's defined by. And finally, what happens, say, if we want to decrease the concentration of ammonia? So in this case, ammonia is a gas in the Haber-Bosch process, or the Born-Haber process. And if that's the case, we could potentially cool that reactor quite a bit and liquefy this, turn from a gas to a liquid, and that would pull it out of the reactor. If that were to happen, then the concentration would start to decrease for our ammonia. So that value starts to decrease. If that decreases, then the overall value of K starts, or Q starts to change, and now the whole system needs to start to move back to the right to make more of that ammonia and to decrease the concentrations of these two things such that the ratio is preserved. So it's all quite logical how the Le Chatelier principles apply.